And at the very end of the class yesterday, we were looking for the DFE implementation with a faster first step close loop. Okay, DFE implementation with a faster first step closing. Let's say faster first step loop closing. Okay, and the main observation in the conventional implementation is that at the output of the channel you have a GM block which amplifies the signal, and then the load resistance and the load capacitor CL. All the tap nodes are actually summed up at the output of the GM block. This, which I have shown here with RLCL, this is preamplifier, and this is a clock comparator. This is block W0, and let me just write it here. Okay, so you have actually a flip-flop at this node. W1 and so on. So this is a conventional implementation which we have seen, and we said that in place of going through the whole loop to the input of the comparator, we can cut the loop short here and connect this node directly to this node. So this will speed up the first loop. So let me just draw the modified version of the new implementation. So you have termination resistance here. So let me now call this as GM1. Now this is the summing loop for all the other taps. Let's do it that way. And then you have a preamplifier. So let me say that preamplifier is also a GM block. So you have GM2 output, and the first node is, so first node has some capacitance RL1 and CL1, resistance and capacitance. Similarly, the second node will also have some resistance and capacitance, which is this capacitance is not from all the taps which are summing previously. So let's say this is RL2 and CL2, and this input goes to the comparator. So the clock comparator at phi, and then you have W0, which is summed up at this node, and rest all other taps are still summed up at, sorry, there was a flip-flop in between. Okay, so this is the modified version. Now let's see how the cancellation happens now. So let me call this node as V sum 1, and this is as V sum 2. Okay, and this one is V in. So V sum 2 is GM2 times V sum 1 minus your IDFE, the first tap closing, right? That is, let me call that as a current is IDFE first tap. In this case, is this goes into your RL2 by 1 plus SCL2 RL2. Now VS1 is equals to your GM1 times V in minus IDFE from all other taps, let's say. IDFE X here, where S is basically 2 to all the taps which you are having in the system. Minus IDFE 1. Sorry, there is another, for this thing, you will have RL1 by 1 plus SCL1 RL1. Okay, minus IDFE 1 times RL2 into 1 plus SCL2 RL2. Okay, so now I split this V in as V cursor plus VISI. So then it will be GM2, GM1 times V cursor. So let me just write it directly here. This V in 1 is equals to V cursor plus VISI. Okay, so this is V cursor times RL1 by 1 plus SCL1 RL1 times RL2 by 1 plus SCL2 RL2. Okay, and here the assumption is that your GM2 GM1 times VISI minus your IDFE X times RL1 plus SCL1 RL1 minus IDFE1 cursor plus ISI. So this will be, sorry, here is another GM part here. GM2 is equals to 0 in the 1 bit period, whatever value it settles. So if you say that it settles all the value, settles to the maximum value in the bit period, then GM2 GM1 VISI minus GM2 V is just, let's see the units, RL1 into IDFE X minus IDFE1 is equals to 0 after settling. Oh, there is RL1 here also. Okay. So now the coefficients needs to be matched. IDFE1 and IDFE2 has to be matched as per this equation. Okay. So this surely fasten your first step loop. Now, which loop is the next important one? So, okay, let me first say this. Here, CL2 is mostly the capacitance of the comparator. Capacitance is okay. CL2 is a consists of input capacitance of comparator plus your output of capacitance of preamplifier plus your output of the summing tap, first tap. Okay, whereas CL1 is a capacitance due to preamplifier, capacitance due to the GM or the node which is feeding into, and all the taps which is coming there. Okay, so that capacitance will basically keep on increasing as you keep on adding more taps for the equalization. So this is input cap of preamplifier plus output of GM1, output cap of GM1, and n minus 1 times capacitance of each tap. Okay, The one tap is summed up at the other node. And the hope is that the time constant which we have chosen right now for the preamplifier, time constant or settling time of preamplifier, which is, let's say, tau preamp, is equals to RL2 CL2, should surely be lesser than time constant of the previous settling node, which was summing node, which is actually your RL1 CL1. Okay? If I cannot satisfy this, then there is no point of closing the loop, closing the shorter loop. Okay. So now the which other loop becomes important after the first tap closing? The second tap closing becomes important. So it's like if you keep on, let's say you now keep on doing the similar thing with the second tap. You separate the second tap from the rest of all the tap. Then you will include another summing node in between. But the thing is, this will just keep on increasing the, it will keep on increasing the complexity to the architecture. So you need to trade off with that also. Now, yeah, I'm basically one summing node, then you have to sum a different, routing will become different. So normally you do not go beyond one or two tap closing with a separate loop. Yeah. Pardon? Yeah, so the thing is, that point is all valid till the time I say that the signals which I am treating here, this d of n minus 1, sorry, d of n minus 1 is a digital signal. So the starting point was that the comparator is working with the analog input, which is smaller, okay, and the output is digital. So whether I go from the second tap to the first tap, if the input is digital in both the cases, then what you are saying is right. So, okay. So the starting point was that the comparator which I am using, let me just say, the comparator which I am using from clock to Q, V in to V out, right? This delay is different from a flip-flop delay, V in to V out. Okay? These delays were different, and that's why we said because if the delay of the comparator is more, then I have to look for that. The reason was that in the comparator case, Vn is a small analog input. Okay. So you have a small analog input, you have to resolve to some digital bits. That's why you take more time. We will see in any of the comparator topology, you will see the difference. Okay. The other in the case of flip flop, Vin itself is a digital input. Digital, or let me just write as a full swing input. Okay. So for full swing input, whether you go from the second tap to the third tap or third to fourth, it will remain the same. So the thing is, the idea of closing the second loop, the second loop needs to be faster, doesn't arise till the time you maintain that V becomes digital after the comparator. Okay, but what happens is, if you are operating it at a very high speed, it will take some time for V to, means even the output of the comparator will not be digital. It will be some swing, but not still to the full scale. So it may take the next flip flop again to amplify to full scale, and then you have the full swing at later on. Okay, so that's why I'm saying the second tap closing comes in very of the high speed architecture, where the second tap closing becomes important because the signal input is not the full swing yet. Okay, so if you want, have you seen any kind of a comparator or a flip flop topology? Any kind of comparator circuit? No. So I'll show you one which can be where what happens is the comparator and the flip flop are same block. It's just used for a different purpose. Okay, and that is a strong arm It's called as a strong, not a strong one, let me just say, sense amplifier based flip-flop. Sense amplifier based flip-flop. And let me just draw it and then explain, then you will know how this can be used as a comparator and a flip-flop both. And this is quite often used. Okay, so here you have so this is phi VIP, VIN, and this can also be termed as, let's say, operating at phi bar. Okay, so let me just mark the node as VON and VOP, and this is, let's say, VX, VY, and this is V source. So this is a clock comparator which has an input pair as VIP and VIM, so M0 and M1. Okay, let's call this as M1 and M2, and this is M0. Okay, so do you see, let me just identify the input, the tail current source is actually a clocked NMOS transistor. Okay, and at the output VOP and VON, they are also clocked with the outputs of PMOS is a clock there. Okay, so now when phi is equals to 0, let me just ask this, when phi is equals to 0, at that time your bottom transistor is off. Okay, and what will be the output node? Can you say output node? No, two output nodes. This is a differential system, right? So VOP and VON will be reset to VDD in this case. Okay, both are VDD, and VS will be pulled up to some common mode potential, right? Now what happens is, so let me just plot the waveform also. So you have, let's say this is the clock waveform. Let's draw it more properly. So okay, so let's say this is the clock waveform. So I have VOP, VON. The time when phi was 0, that time VOP and VO1 both were VDD. Okay. Then what happens? As soon as your clock goes high, VIP and VIN. So let me mark also VIP and VIN. So let's say VIP. So let me just say VIP minus VIN. So let's say this is high, not high here. So something as VIP. Let's say this is VIP and VIP. Okay, just for a mistake. Let's say this is VIP and this one is VIN. So same, I'm using the same color for the polarity. Okay, let's say this is VIP and VIN, something in between. Right. Now what happens when the clock goes high, VIP and VIN, depending on their differential voltage. So let's say VIP is high, then VX node potential will come down. Because it has means both Vx and Vy both will come down when you switch on, but Vx will come down more because the input gate drive is stronger. right? Then what happens as Vx comes down, you see the cross-coupled inverter NMOS. So let me just mark this one. Okay. Now this NMOS source goes down more, so it is more active. Okay. So the thing is, the VON node will go down. So both VOP and VON node goes down. So this node also goes down. This node goes down faster. VON. Okay. Once these two nodes goes down, they develop a certain potential difference VOP minus VON. Okay. And as soon as you develop a difference, this inverter, cross-couple inverter will put a positive feedback in the system. Okay. So when it puts a positive feedback in the system, what happens is VON goes down faster and VOP actually resets to VDD. So VOP minus VON develops this potential difference. So if you look at the difference VOP minus VON, it will be something going down, increasing. Sorry, this is the difference, right? So let's say I'm plotting the mod of this. The difference was 0. It will initially increase in a more of a linear fashion, and then it's a more of an exponential rise because of the positive feedback in the system. So you have a small, so now think it in two ways. You have a small input, you compare the differential signal and generated the full swing signal. Okay. Now this full swing, and you know that this full swing signal is going to be reset to VDD in the reset phase. Okay. So I need to latch these signals VOP and VON such that it remains valid for the one whole clock period. And the way to do is using an RS latch. So this is VON, sorry, you have VOP and VON, and let's say this is equals to Q and Q bar. So this latch, if you look this NAND based latch, when both VOP and VON are high, it will hold the outputs. It's a NAND based latch. Okay. Whereas as soon as your input changes the signal, then this will change the output accordingly. So in a regular, in most of the CMOS amplifier, the flip-flops, you use this kind of sense amplifier followed by an RS latch, and it acts as a comparator which gives you a 1-bit output resolving a very small differential input. Okay, now the thing is the same comparator can be used as a flip-flop also if you think. If the inputs are large enough, if VIP and VIN are sitting at 1 and 0, then the discharge rate initially will be very fast. So will be the regeneration, right? And once you always have this constant 1 and 0 as an input voltage, then for all the flip-flops, clock to Q delay will be the same. So if you are using these kind of flip-flops at a higher speed, you will see after a, so let me just tell you this, that if you have used this kind of flip-flop, okay, so all are clocked at 5, and this is input VIN. So when VIN is small, so output of Y1 will be degenerated to a closer to the rails, but maybe not enough the rail. So if I am having, let's say Y generated something kind of this, in case of Y1, Y2 might be higher. And once it reaches the full scale, the following blocks will always have the full scale. Okay. So closing the second loop, whether it is required to close the second tap loop with a faster loop depends very much on the speed. But first tap, most often you need to do that. Okay. So, so in all these cases, you have seen that the clock which I have used or the time period which I have used for settling is 1-bit period. Okay. and I am operating all the flip-flops at the data rate. So let me ask you this. The way DFE function is functioning here, in very literal words, that I take a decision on V sum at rising edge of clock, right? That's how I get my bit Dn minus 1. Okay, so look at what happens during the whole bit period. At the very instant of the clock, rising edge of the clock, I take a decision whether the bit is 1 or minus 1. The second thing I do, I add or subtract plus minus IDFE from VSUM for following bit. Okay. The important point is that you subtract either plus or minus. There are only two values which depend, which are you do, right? Then you allow VSUM to settle. And then compare the next bit, then estimate the next bit, you can say. Next bit. Okay, this is the regular operation which we have seen. At the clock edge, you decide what the value is. Based on that decision, you subtract plus minus IDFE, allow it to settle, and then take the next bit decision. Okay, so can you think of rearranging this thing to speed up? So the information, my hint to this is the information which you have is you are subtracting plus or minus depending on a bit. So think it this way. First you have to take the decision bit, then you have to subtract. Okay, and when then the subtracted value is greater or lesser than the threshold, you decide plus or minus. But the only thing is you are always subtracting plus or minus. So the other way to look is, so let's say you are having a VSUM node and which goes to two blocks. And in one block, let's say this is another GM, the same GM block. In one case, I always add, let me just plot it clearly. Here I add IDFE and here I subtract IDFE. Always. Then whatever is coming, and then this is a comparator which is working in like always. This is not a clock comparator. This is a comparator which just keeps decide what the value is. Okay, and then I choose which of them should I choose depending on my previous bit. So my select signal, ideally you can say my select signal is so whichever the signal is, t of n minus 1 is acting as a select signal for a mux. So the thing which I have used here is that I am always subtracting either of the two values. So I can very well subtract it without depending on the decision whether I got a dn and dn minus 1. Sorry, dn is plus or minus 1. I subtract these values, let it settle. Means the subtraction is not based on the decision what you make before. Once you have the subtracted and compared value, so you can say I have a, once you have the subtracted and value, then you just choose which value do you want depending on the previous bit. So here if you see the time, so this is a 2:1 mux, this t mux is the time which I am relying on. Means as soon as the select signal comes, after the select signal it should be there. Pardon? This one will be on the V sum 2. This is for the last step which I am considering right now. So in this figure, right, which you have seen before, this is V sum 2 node. V sum 2 is the rightmost node, right here? Yeah. So for all other tabs, you can do still the V sum 1. So last step is the most critical tab for the closing, right? So I can, on the last step, I can do this. In place of depending on the clock to queue comparator delay, now I am only dependent on the tmux delay. Okay. Pardon? Yeah. This loop still has comparator, so that comparator delay will be there. So, okay, let me just bring it back here. So think about it. You got a dn minus 1. So you start at a t instant. So if dn minus 1 comes at certain clock, or wherever you get a dn minus 1, from the dn minus 1 to the next instant where you are going to get the next bit. So for the next bit, you have to subtract either plus IDFE or minus IDFE. Okay, so let me just wait it. So let's put it this way. Just a minute. I think this will make more clear. Pardon? So think about it. Once you get a current bit, right, you have to sample for the next bit. And for the next bit, you are already subtracting you are already subtracting the current depending on the bit. Already is summing subtracted from this circuit. And just based on the bit, you select whether I take the higher or the lower. So the difference here is here the comparator is not a clock comparator. It is still giving you large swings. Do you get this part? After preamplifier, yeah. So okay, this thing is. Let me put it this way. If you are okay, so let me draw it completely. So pardon? It's only through W1. IDFE 2 is the only current which I am using here. It's a W naught. It's a W naught current. Yeah. So let me just draw the whole one. I think that will make a more. So you have this is GM1, and then so in the previous case, you see, okay, what was there in the present in the previous case? Let me just say, in the previous case, you had only this part, right? And this IDFE, whether it was plus or minus, that was dependent on what was your previous bit. Now what am I doing is I am just splitting that path into two paths. Okay. And in one case I am adding the current, in one case I am subtracting the current, because I know in the end I have to add or subtract only two values. So I do that already and I compare that. Now this comparator is not a clock comparator. This comparator will resolve the input to a large output. For simplicity, you can say that here. Okay? Yeah. No, there is a settling time. So as soon as you, so the thing is, as soon as we are closing the first loop shorter, that delay part is we are taking care of, right? But there is a settling time for the RC time constant also. Now for that settling time of the RC time constant, now we are not dependent on that. Okay, so the thing is, all the loop closing thing is that your T clock to Q plus T settle plus T setup, that should be lesser than 1 bit period, right? In the previous case, what we addressed was T clock to Q. We removed that, sorry, that was also going T clock to Q and the amplifier and the settling both. Here we are targeting the settling. Here we are targeting the settling also, because you are already, the settling in starting instant is not dependent on the previous bit. TCQ will not be. In place of TCQ, now you will have a TMUX coming there. So as soon as the select signal of the MUX comes in, after how much time do you have the next output? So if your TMUX is actually larger than T clock to Q, then there is no point of using this. Okay. Yeah, we do have the settle time. Means if you say that RLCL is pretty large, even when you are having a IDFE current there, it will not settle to the value which you can take from the MUX. Yeah, this is, you have T comparator. I can just have the, you can say. So if you take the whole loop, let me just start. Where? In place, so the one thing you notice, in this comparator, you are not having any clocked value. Whatever input gets in, that is getting resolved to a higher swing or lower swing. Okay, so there is no starting from a clock, values are reset to 0 and then the outputs first gets like generate, that value is first it basically gets amplified and regenerated in the comparator, which I have just shown you here. You will use a different type of comparator in this. No, why? The comparator which you have used before, that comparator can't be used here because that comparator needs to be clocked. That comparator output is reset at every negative edge of the clock, right? So this comparator is, you can say this comparator is just amplifying the signal to a larger value without getting it reset. So it again depends on the very much design of this comparator, that if the comparator is taking a lot of time to regenerate a small value to a larger, then this will not work. And this will have the problem that, okay, in the previous comparator, you see that the outputs are reset to VDD. So one bit doesn't spill to the other through the comparator. Okay. Whereas in the comparator where you are not resetting the output, if the previous input was large enough, then the previous output was large enough. Now if you change the polarity of the output, it will take maybe a longer time to reset to change the comparator output. So that you call as a data dependent ISI, where previous bit is going to affect the next bit output swing. So that problem will arise here. But the whole thing is we are trying to overcome this t clock to q delay with a delay of t mux, which is lesser than t clock to q of comparator. So this thing is called as loop unrolling. You can say loop unroll DFE. Unrolling is like whatever the previous loop was, you just duplicate it or unrolled it. Okay. So, but in all these cases, what we have considered so far, you see all the flip-flops and everything is still operating at the bit rate or the data rate, right? Now, the question is, can we always operate the thing at a bit rate? So if you increase the speed, the same circuit may not work at all. And the reason you can say this, that's why I showed you also this, that let's say the starting point in VOP minus VON, if my bit period is something here, if the bit period is very small, then I cannot even enter into a regeneration region, or my regeneration will not be even large enough to give you some finite swing. So it's like you cannot operate the flip-flop at that high speed. And if you cannot operate a flip-flop or a comparator at that high speed, what should be the option? Pardon? Huh? I didn't get it. So it's like something as you say, it's like a subrate. When you say a parallelized architecture that is operating at a lower rate, right? That's what you meant, or something else? So if any of these digital blocks you cannot operate at a data rate, then you go to a subrate architecture, which I think this is what you have used in case of CDRs, a half rate CDR or a quarter rate CDR. Now, the same thing will happen here, a half rate DFE or a quarter rate DFE. But now I will ask the question, do you think that a half rate DFE, this basically this time limitation will change or it will remain the same? Any idea? It will change? Huh? So we need, so let me just rephrase it. So you're saying we need a data at every clock edge, every bit rate, right? You should sample the data at the data rate. The only thing which we are doing by parallelization, let me just put in a simple thing. Let's say this is your data detector. You have a clock, D in and D out, and on this you have phi bar. So this is D even and D odd, right? In the previous case, you are having only a single flip-flop operated at phi D in, and this is data. And if let's say this clock rate is 5 gigahertz, means 5 Gbps data rate, this is 2.5 gigahertz, right? So the flip-flop speed has gone down. And the data at the both are basically at 2.5 Gbps of data. Now if I have to go to a lower data rate because of the speed limitation on a flip-flop, is it going to change the set? Is it going to change the DFE loop? No. Pardon? Yeah. So the thing is going to you're right, going to a basically a half rate is not due to because you want to do the DFE becomes easier. It's a limitation that you cannot operate the circuit at that high rate. So that is, I will show that this simple thing. So let me just show that without like a conventional one. So you have, so This is now what changes here is this is phi bar. Let me write it as phi bar, that will be better. So this is phi bar and this is phi. Okay. So now these two comparators are clocked at half the rate as you have seen before. And let me just show the first step one. So then you have this thing, let's say as W naught, both of them. And where should it add to? So this one has to go where? So let me call this as V sum 1 and V sum 2. Where does this output needs to go? The output, let me name that also. This is, okay, pardon, just a minute. This is, let's say, D even, is a signal, right? So this one is D even and this is D odd. So where does the output of this D odd tap should go to? V sum 1, right? So this one goes here and this output goes, oh, what happened? V sum 2 and this output goes here. Okay, so this is only for the first step which I have shown, but how will you arrange the other taps? That will be there. So by doing this, now you see, right, when the clock comes, it has to give the value which should, with respect to this clock, it should settle within the half the period because your next sampling instant is coming half the period. So the time, the limitation on restriction on this T clock to Q plus T settle plus T setup is not, you do not gain anything here. The only thing which you gained is that your flip-flops can now operate at half the rate. They have more reset time the way I have shown you the flip-flop or comparator. Okay, so it basically reduces, if it is basically reducing the T clock to Q because you are operating at half the rate, then it is better. And it can reduce because now you are having a more reset time, you reset to a VDD value, you start with more fresh state, whereas in the previous case you may not be able to reset to a final value also. So from that point it is better, but this 1 bit period limitation doesn't go away. So this one is half rate DFE architecture. Now, can you think on if I on half rate I applied loop unrolling? This will become more complex. Whole of your loop unrolling will come in both the parts, right? So things can become more complex if you try to have loop unrolling, closing first step, and apply half rate. So you go and do that only when it is necessary, when you cannot do the full rate architecture, and when the power consumption in full rate is quite a lot. Yeah, the scalability to different clock frequencies works pretty well for a lower frequency, but at a high frequency they do not. And the reason is all your capacitance. So let's consider this thing, right? I mean, it's a good point that the sense amplifier flip-flop, right? If I just scale the frequency, it should be able to work. There is no problem at all. But from the very point where I showed, if the bit period comes so close that you are not even having a regeneration, right? So it's like you are having this flip-flop. If you just, the ideal thing is if you just increase the frequency, it should be able to do the same function, just consume twice the power. It should not be anything more. But if you are not able to do the whole process like amplifying and regeneration within this flip-flop, then it is not even operating as a flip-flop. Then you have to spend extra power in it. So that frequency scalability doesn't go that well at a higher frequency. At a lower frequency, it might be still good. Okay. So now whatever we have seen is like the more the number of taps which we want to cancel, the more capacitance will come at the summing node, and it will be a settling issue and closing the first loop thing, and this also adds to the complexity, right? And all of this is because we are trying to do a FIR implementation. Whatever the ISI, we just sum up the ISI and cancel it, right? So there is another kind of architecture which is called as IIR DFE, and this is not this is applicable only to a very specific kind of channel loss, but it is nowadays quite often used. So let me show where it can be. So you have, let's say, this is the channel response, okay, and I have the main cursor, and okay, I'm showing a lot of ISI, but let's say this is the case, okay, and let me just call this as H naught, H minus 1, H minus 2, H minus 3, minus 4, and all. And you have many taps. If you want to do it with a regular FIR, you need to add up all these steps to the summing node. Now, if I come and say that this part of the response, if you just take this part of the response, this part of the response can be approximated with something as e power minus t by some RC. And this is a specific case. If this part of the response can be approximated as e power minus t by RC, then what do you think can be used for cancelling the post cursor ISI? Huh? Charge capture and then release the charge, right? Decay. So that is specifically what I can do is, let me just plot it here, that let's say I have RC which is modeling this kind of response. This is R and C, and here I so let's say if this bit was 1, here if I apply a minus 1, so let me just draw this also, and I apply this bit, so let me call this as a D of n minus 2, because I am starting from H minus 2, right? Or wherever you can say, whichever ISI you want to cancel. So if you apply this response, this kind of pulse at the input of an RC filter, the output of this is going to be something kind of this, right? It's a pulse thing, so it should be something kind of that. Now, if I can match these with H minus 2, H minus 3, I am done, right? Huh? Pardon? Yeah, opposite polarity. So that you can take care of. Means the only thing means you are matching this response. That is a subtraction, right? Earlier I was doing a subtracting the IDFE current, and now I will see the curve depending on the current bit. I can just flip the bit while giving while cancelling the SI. So that you can say is something. The implementation will be GM block. You have RL and CL, and then a comparator, let's say clock comparator, and then the thing is you have this RC kind of input, and that goes and summed up at this node. Okay. In this case, you can cancel all the kind of means this is like an IAR cancellation. So you are cancelling all the taps with using one only. And this thing is normally done starting cancelling from the second post cursor ISI. So the reason is you can say if not, why not from the first post cursor? Because as soon as you get the bit, you may take some time to get start the pulse or something. So H-1 might be difficult, but that's still possible. That is also being done. But H-2 is for sure you can do it. That you can, so the thing is you can always have followed by a GM block. So this is very like just a block diagram. You have an RC thing, you can have a GM current in response to that, and then you can summon. Which GM block? The first one? The first GM block you need. Okay. Okay, the first GM block you have to amplify the signal to a certain value. It is doing that part also, right? In this case, okay, let me just, if you do not use this GM block, let's say, right? Then you are going to come up with this channel termination and the impedance which is coming at the summing node. You have that separation. You have that separation, you are amplifying the signal also to a certain minimum value. Okay. So this one is called as IAR DFE, and this is also now quite regularly used, but this can only be used if you can approximate the channel with an RC response. And that is why this is mostly used for on-chip links, because on-chip links you are having any metal wire piece you can do that. Okay, so these are all different kinds of DFE which we have discussed so far. If you have any questions, you can ask, and then I think the next class we will start with the DFE adaptation. Let's stop here.